find a confidence interval, we are establishing a particular claim in a situation where one may not have existed. If we don't know anything about a particular population parameter before, we could point to a confidence interval and say, oh, hey, now we know something here. But suppose we already do know something about the particular population or situation, or at least think we know something about that population. In that case, we are able to either check that pre-existing understanding to see if something has changed or is inaccurate, or, if we're running an experiment, we can find out whether a particular treatment may have a measurable effect against a certain set baseline. This procedure is called a hypothesis test, a comparison of collected data against some pre-existing and reasonably accepted standard. We use the techniques and concepts we have discussed so far: simple random samples, measures of centers and spread, probability distributions, to find out whether a particular result is so unlikely given a particular standing belief as to actually cast doubt on that belief. And these seemingly vague terms, belief, doubt, likely, and unlikely, are essential for both understanding a hypothesis test and understanding the real limits of hypothesis testing. First off, this word hypothesis. You may remember it from a science class a while back, and in certain ways, hypothesis testing does have similarities to the scientific method. A hypothesis is a belief or a formulated idea. Whenever we perform a hypothesis test, we need two of them: a null hypothesis and an alternative hypothesis. A null hypothesis is some standing belief or measured value, widely held and assumed to be on some level true. The common understanding that the height of the average American male is 5'10" is a null hypothesis. The content statement of 12 fluid ounces on the side of a soda can is a null hypothesis. Any general claim of a measurement, either a quantity or a proportion, can be construed to be a null hypothesis. There is exactly nothing that says that we have to take a null hypothesis at face value. Indeed, we are in many ways encouraged to dispute them and see if they are valid. This dispute is called an alternative hypothesis. An alternative hypothesis does not state a particular value in place of the null hypothesis. We aren't going to say, no, that can only holds 11.5 fluid ounces. An alternative hypothesis merely says that the null hypothesis is not true. We can also use this null hypothesis alternative hypothesis setup to measure changes in an experimental setting. The null hypothesis is some measured variable without a particular treatment, almost a control. The alternative hypothesis says that the variable will change in a significant and measurable way. A particular cholesterol level will go down, a corn plant will grow faster, a person will solve a puzzle faster in response to some treatment. An alternative hypothesis can dispute a null hypothesis in one of two ways. If the alternative hypothesis simply states that the null hypothesis is incorrect but does not specify whether it is too low or too high, it is considered a two-tailed alternative hypothesis. If an alternative hypothesis makes a specific claim about the direction of the dispute, this is a one-tailed alternative hypothesis. If I'm looking at a particular measurement and checking to see if it's accurate, I'm usually setting up a two-tailed alternative hypothesis. If I'm looking at something and saying, yeah, no way that thing is as fast as this guy says it is, that's a one-tailed alternative hypothesis. In either case, the calculations required to resolve this generated dispute are straightforward. We have some numeric value for the null hypothesis, either a proportion or a mean. We collect data according to standard procedures, simple random sampling and so forth. We compare our point estimate to the null hypothesis value by setting up a probability distribution of sorts around the null hypothesis value itself, and seeing how far away the point estimate is from the null hypothesis value, and in doing so, finding out how likely we are to see that particular value given that the null hypothesis is correct. This is where the conceptual work gets interesting. We are obligated on a certain provisional level to assume that the null hypothesis is true. We then compare it to our data, which is definitively true. Data is real, substantial evidence drawn from the population under consideration. Our unit of measurement for this comparison is the standard error, as previously established for either categorical or quantitative data. If the point estimate is far enough away from the null hypothesis value, that is, if the likelihood of that point estimate occurring Given that the null hypothesis is true, is very unlikely, we have evidence to dispute the null hypothesis. In proper language, we are rejecting the null hypothesis. On the other hand, if the point estimate is decently close to the null hypothesis value, we don't have grounds to dispute the null hypothesis. That doesn't mean that the null hypothesis is true. It's just that we can't argue against it with any force. Given a close match between the null hypothesis and the point value, we fail to reject the null hypothesis. A null hypothesis can never totally be proven true. It can merely not be proven false. And one single rejection is not enough to change the value of a null hypothesis, but it is enough to call that null hypothesis into question and doubt or dispute its legitimacy. Given that our result is some meaningful distance away from the null hypothesis, how much of a difference is enough to cause us to doubt the null hypothesis? The short answer is that there is no definitive degree of difference. Thresholds of significance to reject or fail to reject, or the degree to which a particular result has to differ from the null hypothesis, will always be arbitrary. But, in most cases, we can establish a certain threshold quantity, an alpha. Alpha is an arbitrary but well-considered probability level that we use to measure the likelihood of a particular result. If the likelihood of an outcome compared to the null hypothesis is less likely than a stated alpha, we have reached a certain level of statistical significance and can claim that our result is justification to reject the null hypothesis. In use, an alpha is very similar to the equally arbitrary but still well-considered degree of confidence in a confidence interval. The use of alpha depends on how we construct our alternative hypothesis. If we form a one-tailed alternative hypothesis, the alpha value is drawn on the appropriate side of the distribution. But if we form a two-tailed alternative hypothesis, the alpha is split between the high side and the low side, much like with a confidence interval. By extension, it is a bit easier to reject the null hypothesis on a one-tailed alternative hypothesis, although one has to be informed or bold enough to make the correct call in the first place. So let's run through a super quick setup of this arrangement. A certain null hypothesis exists and has a set value. We collect data and formulate a point estimate. We find the difference between the null hypothesis value and the point estimate measured in multiples of the standard error. Convert that z or t value into a probability of occurrence given the appropriate distribution. If the probability of occurrence is less than alpha, we reject the null hypothesis. If the probability of occurrence is greater than alpha, we fail to reject the null hypothesis. In all, it's an elegant and logical system. There's only one problem. It depends on the sample being a true representation of the population. It is entirely possible that we will randomly select a sample that either supports the null hypothesis when it shouldn't, or directs us to reject the null hypothesis when we also shouldn't. The first of these arrangements, the rejection of a correct null hypothesis, is called a type 1 error. The second, the failure to reject an incorrect null hypothesis, is a type 2 error. Both of these are simply consequences of the unavoidable vagueness of the simple random sampling process. So yes, this is a pretty serious amount of conceptual material to keep in mind when performing these statistical operations. Fortunately, the implementation of these processes is much more straightforward.